Welcome. In this lab, we're going to talk through the spectrophotometry lab that we did and hopefully help you interpret your data and understand what is going on with this lab technique. So I'll be able to understand what spectrophotometry is and how we use it to figure out the concentration of an unknown. So there we go. So in this lab, what we're doing is we're looking at the substance yellow dye number 5. That was the thing we were analyzing. And the idea behind spectrophotometry in general is that we can use the color of the solution to determine the concentration of a solution. And in order for that to work, we need to have some solutions of known concentration. So in this picture, we can see we've got solutions with known concentrations. And then notice how they're different shades. So the more concentrated solution, the darker it appears, and the less concentrated, we refer to this as being more dilute, and this over here is more concentrated. So the more concentrated, the darker it is, the more dilute, the lighter it is. And if we have these knowns as a comparison point, then if we come along and encounter an unknown where we don't know the concentration, we can try and match the color to one of these knowns and make a guess as to what the concentration is. So this one maybe it appears to be similar to this shade, so maybe it's 0.0001 molar yellow dye, but maybe it's somewhere in between. It's really hard to gauge this just by looking at it. So that's why we're going to use the spectrophotometer to get a more precise measurement. So the spectrophotometer essentially gives us a reading of how dark our solution is. And what it does is we shine a light at your sample, and then we measure out how much light comes out the other side of the sample. And that measurement is going to tell us how much light is absorbed. And when the solution is darker, that solution is more concentrated. And if we think about what that means, it has a higher molarity. Remember, we use molarity to measure concentration. And if it's darker, it's more concentrated, it is going to absorb more light. So it's going to have a higher light absorbance. So the idea here is that when a solution is more concentrated, like this one over here, it looks darker. The reason why it looks darker is because this solution is absorbing more light, because there's more of those dissolved particles there in the solution. And so our goal here is in our lab, we're going to try and figure out the concentration of our unknown. That's either Gatorade or Mountain Dew. We're going to test both of those things. And we're trying to figure out what is the concentration of yellow dye in the Gatorade and Mountain Dew. So in order to do that, we need to make solutions. We need to make our knowns. We need to make some solutions with a variety of molarities. So we have several different shades of yellow. So that's what our step 1 is. We're going to make various solutions. And so at this part, your group split into 4 different tasks. Each person made a different solution, and we all made solutions in a 100 ml volumetric flask. And so we all took the same solution to dilute. So our initial molarity was 0.123465 molar. That's what we refer to as our stock solution. That's what we're trying to dilute. And we're trying to dilute it to a volume of 100 milliliters. So what that math would look like, let's just go over one sample, is if my initial molarity is 1, 2, 3, 4, okay, gotta count the zeros because it's easy to lose track of them. That's your initial molarity. My initial volume is, I don't know. And then my final molarity is going to be 0.123445 molar, and my final volume is 100 milliliters. So these will be very similar calculations for all 4 of these solutions. So you're going to rearrange and solve for V1. So you're trying to figure out what volume of your stock solution do you need to dilute in order to make that diluted solution. 1, 2, 3, 4. You gotta be careful with your zeros here. I know there's lots of zeros here. This yellow dye number 5 is pretty potent. You don't need very much of it to turn the solution pretty yellow. So you're gonna calculate what volume you need. You're gonna make your dilutions. And then the part 2 of the lab, and this is what it looks like in the directions in your lab book, is to figure out what wavelength of light your solution absorbs. Because we said that your solution will absorb light, but it turns out there's lots of different kinds of light, right? Like the white light that's coming in through the window is actually made of a lot of different colors, and we can describe the different colors of light using their wavelengths. And so this is what your graph should end up looking like after part 2. You got a graph that looks a little bit like this. And we'll notice that yellow solutions absorb blue and purple light pretty well. And if you look over the data table, or if you just want to kind of eyeball it, this is 300 nanometers. This is 500 nanometers. This is 400. So it looks like our solution is absorbing really well at maybe, around 425 nanometers. And it turns out that corresponds to like a blue/purple light. And what we'll actually notice if we ran this with a bunch of different colored solutions is we would see that if a solution appears yellow, that's because it absorbs purple light. If it appears purple, it would absorb yellow light. If a solution is blue, it would absorb orange light. So the light you observe, that's the reason why it appears that color, is because it's absorbing the opposite color on the color wheel here. So notice how our yellow solution is absorbing light at about 425 nanometers, which is that purple color. So that was, part 1, make solutions of some different molarities. Part 2, figure out what wavelength of light those solutions will absorb. And we discovered that's blue-purple, which is 425 nanometers. Then part 3 is we are going to measure the absorbance at that wavelength, 425 nanometers, because that's the color of light it absorbs really well. And we're going to measure the absorbance of these 4 solutions that we made. So you made some solutions. You're going to measure the absorbance of those solutions. This is where you should be recording the absorbance in your data table. And if you forgot to do that the other day, then hopefully someone took a snip of your data and you still have it saved somewhere. So you want to have your absorbance there. When you get the absorbance and you know the molarities, you'll be able to make a graph. So here's some examples of graphs that some students in your class made. This is one. Notice that when you make this graph, that it should find, when you hit stop collecting data, Logger Pro should find the slope of the line for you. The way they report the slope is kind of weird, the way it's written out. Notice how it says 1.724 E plus 004. What that means is 1.724 times 10 to the 4th. That's written in scientific notation. To write it in standard notation, that's 17,240. So that's what that means. The slope of your line is 17,240. So this is one sample data set. This is a sample data set from another group. This data set I took and I plugged it into an Excel. Notice how the slope of this line is 16,454. And then here's one other group. Their slope was 17,320. So your slope should be somewhere between, 16,000 to 18,000 roughly is the slope we should be getting. And if your group had a hard time getting this graph, then feel free to use one of these sample data sets. So you can, there's some slides in OneNote where you can use one of these samples graphs if you don't have a good slope to work with, because we need this to do the last part of the analysis. So your slope should be somewhere between, 16,000 to 18,000. And why do we care about the slope? Well, this is a linear graph, right? So this is a straight line. And the generic equation for a straight line is y equals mx plus b. That is the general equation for a straight line, where m is the slope of the line. So let's think about what that means in this context. So our y-axis is absorbance. So that's y. And our slope is, 17,000. And then our x-axis is molarity. So we can take this generic form y equals mx, and we can write it as absorbance equals slope times molarity. And the way that we can then use the slope is if we have an unknown substance like our Gatorade, and we're trying to figure out what is the molarity of our Gatorade. Well, if we measure the absorbance of the Gatorade, you can see when we do the math here, molarity equals the absorbance divided by the slope. So if we know the absorbance and we know this relationship here, this slope, we can figure out what the concentration of our solution must be. So you've got a graph. That leads us to the last part, which is measure the unknown. So we had some Gatorade and some Mountain Dew sitting out in the front of the room. If you didn't get the data for that yet, we could always get some later. But you should have some absorbance written down for your Gatorade and for your Mountain Dew. You don't have to like push any buttons, just gotta put it in there and measure the absorbance. And notice how they're not going to be part of the graph because we don't know what the molarity is. So we can't graph it because we don't know what the Y value is. We only know we don't know what the X value is. We only know the absorbance. Okay, so, but you should measure the absorbance of your unknowns. And then once we know the slope of the line and we know the absorbance, then we can do a calculation. So remember, the slope tells us the relationship between the absorbance and the molarity. So absorbance equals slope times molarity. You can rearrange this as molarity equals the absorbance over the slope. So let's say you come and you measure the absorbance of yellow Gatorade, and you get that the absorbance of yellow Gatorade is 0.32. I'm not saying this is what it actually was. I'm just putting an imaginary number out there. Okay, the absorbance is 0.32. The slope is whatever you found on your graph. So let's use this slope right here. That's 17,320. Okay, so slope is 17,320. And what is the molarity? I don't know. So I'm going to use this equation right here. The molarity is the absorbance divided by the slope. And notice how it's a small number divided by a pretty big number. So our answer should be pretty small. So I'm going to do the math real quick. 0.32 divided by 17,320. And I get this. I get 0.0000, so 4 zeros, 18. And that is the molarity, which seems reasonable because we know our original solutions had a bunch of zeros there as well. They were pretty dilute. So it makes sense that our Gatorade is also fairly dilute. Just so you know, your calculator might be set to report answers in scientific notation. So another way in which you could write this is you could write this as 1.8 times 10 to the negative fifth molarity. Or sometimes in your calculator, they might use the capital E button. So it might look really weird and kind of look like this. So what that means, 1.8 times 10 to the negative fifth, the way you would interpret scientific notation, if it's a negative, is you take the decimal and you move it 1, 2, 3, 4, 5 spots to the left. So notice how that looks like this number right here. So that's how we interpret scientific notation. So if it's a negative value, that means you're moving the decimal to the left. If it's a positive value, like let's look over here again at this slope. Notice how, again, right here, they wrote the slope as 1.732 times 10 to the fourth. The way we would interpret that is we would move the decimal 1, 2, 3, 4 spots to the right. I'm going to fill in a zero there. So that is equal to 17,320. So that's how our scientific notation works, just so you know if your calculator is reporting answers that way. All right, so please let me know what questions you have. You can send me a message or stop by tutorial, and hope this helps.